All right, coming back into this first example in the sinusoid application class notes, I did want to talk again about, or kind of go back and talk about the actual units issue that was there. And you saw that when I first graphed this sinusoid and I was checking it, that I originally had my mode in degrees. Of course, and then you take a look at the graph, it definitely does not look like a sinusoid. And when you see that kind of stretched out nature, one of the things that you have to recognize is that you are in the incorrect mode. And I did want to talk a little bit about why the mode of radians is kind of really important as we are looking at these application problems. Now, the reason for that is kind of going back to our idea of trig functions, that if I had f of theta, and let me make myself a little bit thicker here. All right, so if I had f of theta equals cosine theta, think of that as your parent graph. That typically what we had here, our input was an angle and our output was a ratio. Now, the idea here in this angle input, and originally when we started this, our angle input could be degrees or radians. But pretty much from now on, we want to make sure that whatever we are inputting into here is going to be a radian measurement. Now, the reason for that is that, if you recall, this is a unitless measurement, that it is not, that it actually doesn't have a unit. And so what that does for us is that means that when we start doing these transformations, like over here I have this pi over 5 times t, that if I use a unitless measure like that to represent the angle theta, that allows my x-axis to become any unit that I need it to in an application problem. In this case, it's in seconds. So if you think about this, like when I have this theta equals pi over 5 times t, remember that this was, pi over 5 was your radians per second times your seconds. So that creates this idea that when you have that product, that the result is a radian measure, which is what is accepted into the cosine function. And then going on the outside of that, your ratio that you get out, because it's a ratio, has no units as well. It's a unitless measurement as well. And so what that does is it allows the output, the h of t, to take on whatever units the midline and the amplitude have. And so in this case, the y-axis was in feet. So because the cosine ratio has no unit, then we're multiplying by feet and adding feet to it. So that gives us that our height, our output, is measured in feet. So this kind of gives us a way of working with applications where we can set the x and the y-axis to be the units that we want as we're doing it. All right, let's continue down through the problem and take a look at part C and beyond. All right, so we're looking at the first question here is asking, how high above the ground is the rider at 48.5 seconds? So what we know is that we're going to be calculating h of 48.5. So we're basically plugging that in. Now, all of these application problems are calculator problems, so we essentially are going to use the calculator to find that. Now, I will tell you there's a couple different ways to do this. So let's go to the calculator. One is to just use the home screen. So I'm going to quit out of this and go to the home screen. And I'm just going to go alpha F4 and grab my y1, which is where my h function was. And I'm just going to put in 48.5 and hit enter, and it will tell me an approximate value for that. Notice that this is not one of those 5 key points, so I don't get quite as nice of a value. So let's bring that over to the next page, 25.611. Okay, and so the idea is, what units would that be in? Remember, that's an output, and our y-axis is measured in feet, so we're going to add that in. Now, an alternative way to do this, kind of as we are looking at it, is this idea that, remember that there's a periodic function. So if I was looking for h of 48.5, what I could do instead is take out all the repeats and back myself up to maybe the first fundamental period. since it repeats every 10 seconds, we can break this up as 8.5 plus 40, and then we can take out all the repeating patterns, and it would be the same as h of 8.5. And so what that would do for me is if I go back to my calculator, on the graph, you can only trace in the window that you have. So if I hit trace and now type in 8.5, because it has the same value, you notice that I get the same 25.611 that we had before. All right, let's take a look at the next item that they're asking you for. All right, on this one, at what positive time is the rider 88 feet above the ground coming down for the third time? All right, so this idea here, two things kind of what you're looking at. The equation that we're trying to solve is to set our h of t equal to 88 feet, okay? So if I was doing this on a calculator, then what I'm going to do is I'm going to come back here. Oops, where's my calculator? And in my y equals, I am going to go ahead and add, it doesn't really matter y1 or y2, which one you have there. I'm just going to clear that one out because they're both the same graph. And I'm just going to put in the 88 feet and take a look at that as it comes across. Now, remember that what we're looking for is where, let's see, what did it say? It said where you are 88 feet above the ground coming down for the third time, So right now, when you're looking at it, this would be 88 feet going up. This would be 88 feet right here going down, and then up, down, up, down. Now, again, the same thing. I could adjust my window to figure out where I'm coming down for the third time. Now, luckily for me, here's down the first time, down the second time, down the third time. I could just find that intersection point. So I could do second calc and go for 5, the intersect point. Now, we know where that is. You know, come over here. We know what this is. Remember, we were going by increments. We could just put ourselves over there. I like to put myself on the line because it's a shorter distance on a straight line to go across. Because you have to capture the intersection point in your low bound and your upper bound. You have to be close to it. So here's the first curve, and I try to get closer to it. Hit enter. Now I'm on the second curve. Hit enter. And now I'm pretty close, so I'm just going to try to get to where it is and hit enter for my guess. And 26.353. 26 at t approximately 26 point, what was it? 353. 353, and that is seconds. So that's one way that we could do this problem. We could graph y2 equals 88 feet and do second calc intercept. Now, sometimes this is not going to be feasible because it's going to be really far out of the window that we have. So another option is going to be to basically find the first time that it happens. I'll come over here. So find the first time we're at 88 feet and going down, because that would definitely be in your window, and then use the repeating period in order to get the third time that I am coming down. All right, so if we go back and look at the calculator, you can see that I have found that first time at 6.353 seconds. And so if I'm currently at the first time that it happened, to get to the third time, I have to add 2 periods to it. So we would take that value that we just found, and we would basically, sorry, I ran out a little bit of room there, but I'll add it right there. So we take the 6.353, and we add 2 periods of 10 seconds to that, and that's going to give us our 26.353 seconds as well. So that kind of gives you another way of doing that. All right, so now I'm going to pause. I'm going to let you think about this. So take about 30 seconds and think about, how would you tell for how many seconds was the rider above 10 feet. For how many seconds was the rider above 10 feet? What do you think that you could do using your calculator and using the graph in order to help you out? Now, of course, if you guys were in front of me, I would call on somebody and be like, hey, what do you think you should do first? Now, hopefully the thing that you've thought about is that maybe what I should do first is come to my calculator, and instead of putting in 88 feet down here, let's put in 100 feet. All right, and let's take a look at our graph here. All right, now we want to know this idea of how much time, let's remind myself, how much time was the rider above 100 feet? Now, I am going to use the repeating nature of this in order to help me out. That if I could figure out how much I am above in one period, and I also knew how many periods that there were between the 3-minute ride, then I could figure out the total time that I'm above 100 feet. So I'm going to pause, and I'm going to let you guys figure it out. You guys pause yours, come back, and check your answer. All right, so I went ahead and I calculated the intersection point here for this first time that it hits above 100, and then that one. And then I went ahead and subtracted them. So if I go to the home screen, you can see here, there's the first intersection point, and I stored it in A. Then I stored the second intersection point in B, and then I calculated the difference between them to get the total time in one cycle that I was above. And then I multiplied by 18. And the reason that I multiplied by 18 is you can see right here, when I'm asking for how many cycles there are in 180 seconds, that what I did is I divided by 10, which was the period, to get 18 cycles. So I found the value that one cycle contained, and then how many cycles I had, and then I just basically multiplied them out to get my final value of 25.842. All right, and then our last part of this problem, we've been working really hard on this one problem, is to find the linear velocity of the rider in miles per hour. So this kind of goes back to one of the first problems that we did. Now, remember, I'm going to go ahead and grab the angular velocity I wrote earlier, which is pi over 5 radians per second. Okay, so pi over 5 radians per second. And remember that this is just a conversion problem. Why don't you guys pause the video and then try to put your conversion units in. All right, so here you go. You can check your answer, and I do think that's quite fast moving around this Ferris wheel. It'd be interesting to see what the actual speed of Ferris wheels are, because I feel like that's quite a bit. We're going 21 miles per hour, zipping along around that Ferris wheel for that. All right, and then the one key thing here to pay attention to was that the radius of the Ferris wheel was 50 feet, and that's where I got 50 feet per radian. All right, the next thing that we want to do is we want to look at the next example. Let's see if you can work with your phase shift. We want to start his stopwatch when he was 12 feet in the air going up. Think about what you think that would change in terms of his height above the ground. So pause the video and think about that, and we'll come back. All right, so the first thing I did for this problem was I graphed the y equals 12 feet, and I found the time at which we have that place where we want to start our stopwatch at. And then over here on this, what I did is I put the new y-axis at that intersection point. And what that means then is that our flipped cosine graph that we're working on would need a phase shift of going left that value in order to make it start at the right spot. So I just basically added in the phase shift here into the equation. All right, so basically that wraps up example 1 and example 2. And so what I would like you to do is to go ahead and try example 3 on your own, and I will create a key to that and come back in and watch the video for example 3 to verify that you understand what you're doing.